Good morning. So here we are again to talk about how neutron decay cosmology is inevitable. Seems to be the situation. Anyways, good morning. So yes, gravity. Okay, wait. Hydrogen. Slowly works its way down the gravity line. Down gravity. Getting more and more dense until we get to event horizon. Okay, so this sort of this path from least dense to most dense, where concentrations attract, everything moves to catastrophe. It's like there's an attractor, you know. The attractor is time. The attractor is, the attractor is time, which is actually isn't there. It's a vacuum, as you saw in my previous one. So, falls in, neutron star, neutronium, inverts here, which is sort of at the neutron itself, where you've got a double layer. There's like a twist in space-time. The neutron falls through, expands out, turns from a neutron into a proton and electron, and all of a sudden it takes up a whole bunch of room. Whereas here it was tiny. That's expansion. It's that simple. And you have to remember that this, it's not really evident, it's just an arrow, but this is like the metric is getting smaller as we go, right? Like here it's very spatial, it's very low energy. And then the graph would get tighter and tighter and tighter and tighter and tighter until here it's black. It's like as dense as it can be. This is like the little doodle at the bottom here, where it's like, no, this is least dense, more 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 dense. And the way it works is like a halving, basically, right? There's the center point. So let's half again, it's Zeno's paradox of getting more and more dense. That's the gravity well, right? And why? Because as we look at the top here, out here, a Planck is very large. It's a very low density energy. So when you move one Planck, you've moved that far. But as gravity gets higher, you move that Planck, you get that far. You move above that Planck, you get that far. You move a Planck, you get that far. This slope is gravity. It's the change of density of space itself. It's the change of density of space itself. This is why when light travels through a strong gravitational field, it seems to slow down, or it does slow down, depends how you measure. Empirically, it doesn't. It's always going to be moving 1 Planck per Planck second. That's characteristic. It's the way the universe is made. EO and UO are definitely the most significant things we know about the universe and what we derive from them. But this is the slope, right? You're going down the hill, towards singularity. Because that's like the strange attractor to the universe, is itself. There we are again. Right, neutron decays, becomes hydrogen. This hydrogen slowly gets compressed by gravity into until it becomes neutronium. In a neutron star, it does an inversion here. But notice that when you come in on this side, you come out on that side. And this is part of what I think is the, what you do, like, it might have to do with the math of this path of least action. That it's easier to come out as an inversion of yourself after you're in that situation. So you do once as matter and once as antimatter, but every antimatter has its matter anyways, so it doesn't matter because there's only one side to the universe. Yes, oh, and this is the tri-monot, trefoil knot, but it's pulled 1, 2, 3, but it's just the way it's displayed makes it seem like a two-lobed object with this. But this is a trefoil knot, which might also suggest why there's the 3 EM fields all 90 degrees to each other, because that is also part of the trefoil knot in its other mode. Anyways, more neutron decay cosmology.